We're going to look at a few different measures of diagnostics. So whenever we build our regression equation, we need to be able to assess the quality of that equation. So what is the goodness of fit? So I'm going to say that the diagnostics are assessment tools for goodness of fit. And yes, that is a technical term. We do actually use that in statistics, the idea of goodness of fit. Okay, so diagnostic has the word diagnose in it, right? You're trying to diagnose the condition of the regression equation. So we have basically two main measures, but I want to just draw our attention to an example where let's say that we have data points that you could really see that they would all fall perfectly along a straight line. So if I were to come in here and actually perform a regression in this case, I mean, obviously I didn't draw it perfectly, but if it were perfect data, then it would go right through those points. Now there are two measures for talking about the goodness of fit. The first one we'll look at is this thing called r squared, r to the second power. And r squared is a number that's between 0 and 1. And the way I like to think about this is 0 is really 0% and 1 is really 100%. So if you're thinking about giving a grade to the equation for the data points, then you're going to give it a grade between 0% and 100%. The better that line fits those data points, in other words, if those data points fall right on that line like they do in this case, then it would be a perfect fit, and this graph we would say has an r squared of 1 or 100%. It's a perfect fit. Now, as you can imagine, that anything less than a perfect fit is not going to have 100% r squared. Well, let's take a look at what another one might roughly look like. Let's say that you kind of have a pretty good fit, but it's not too perfect, right? Because at this point, you come up with your regression equation, and you notice it doesn't touch all the points. Well, this might have, this is pretty good, so it might have an r squared of maybe 0.85. Well, as those data points become more ovular in shape, if you were to kind of circle them, then, like let's say you can have something more like this, a cluster of points. Well, and you fit your line, this might have something more of an r squared of, I don't know, 0.65, 0.7. Hard to say exactly. But as that oval that you could draw to surround those points grows, the r squared, or the grade that you're giving the fit, goes down. So 85%, this is only a 65% fit. And then, as you can imagine, if you just have this random cluster of points, it doesn't seem to really have a trend. Again, where do you draw your line? Which one of these fits this data best? So this would probably be r squared of pretty close to 0. Okay, so that's basically our way to assess the goodness of fit, based on this measure of r squared, and we'll take a look at an example. The other version, and I'm going to jump to a new page here, is r. You'll notice a number called r, and r is a number that's going to be between -1 and 1. So in other words, it could be negative 0.5, it could be 0, it could be 0.6. Now what's the difference? Well, really the difference between r and r squared is, number one, r squared is equal to this number squared. So you basically get the same number. You square one, you get the other. But the beauty of r itself is if it's negative, then that tells us if r is negative, well, that gives us more information than the r squared, because just by knowing that r is negative, that means that as the input increases, the output decreases. So it would have a negative relationship. This is called a negative correlation. Negative correlation. The reason we call it negative is because as one goes up, as the input increases, the output decreases. And then if r is positive, well, you imagine that that's a positive relationship, and as the input increases, so does the output. So that's really the only difference, and you can still really think about, if it's the closer it is to +1, the better of a positive fit it is, and the closer to -1 that it is, the better the fit it is. Now, anything that's, between like -0.2 to 0.2 is probably a pretty bad fit, but as you kind of get farther out in the negative direction or farther out in the positive direction, that means that the points, tend to be more clustered around this line, whereas with around negative 0.2, what would a negative 0.2 look like? Negative 0.2 would probably just be, maybe a bigger cluster of points, of course, a negative relationship. And what would r of positive 0.2 look like? Well, that would be the same idea, except it would be a positive relationship. So that could be r equals 0.2. So same kind of shape of those points, but different direction of where the outputs are going. Okay, so now that we have that, let's jump back here and take a look at an example. So let's say that our goal, we might be interested in modeling the relationship between two things that we don't fully understand. Like, different people have different incomes, and these are measured in thousands of dollars. So person here would be making $40,000, and then we want to look at how much taxes they pay. But really, realistically, two people making the same dollar amount probably don't pay the same amount in taxes. So we wanted to just kind of get a rough idea of, well, okay, so how much do my taxes go up as my income increases? Well, we probably know that this is going to be, if we were just to guess, it's going to be probably a positive relationship. Positive relationship between as your income goes up, then your taxes probably go up too. So that's probably just our intuition acting here. And we see that as income increases, then so do the taxes. They just continue to get bigger. Well, we want to actually understand mathematically how we could actually model this data. So I've gone over to my calculator. I've entered in my points into L1 and L2. There are my incomes. Those are my inputs. And I want taxes paid to be my output. So I want to be able to plug in an income and get a number of taxes dollars as my output. So I'm going to quit out of here. I'm going to go to my stat calc linreg, and of course I don't want to have to type in the equation manually, so I'm going to do my vars, y vars, function y1, and so this tells my calculator, take the linear regression equation, plug it into the y1 screen, and there we go. So there is the equation. I'm just going to pull up this window here so that you can kind of see that equation would now be plugged in to our this just isn't updated, so never mind, I'm going to take that back. So now we have an equation. So let's just copy this down first. So y equals a, which in this case it's telling us that its estimate of a is 188.19. So we'll just do 188.2. And that's times x plus b. Well, b is negative 2149.5. Negative 2149.5. So I could just do minus 2149.5, and that gives me some information. So now I could go on and interpret this. Well, first of all, input x is the taxable income, and output are the taxes paid, which here it's displayed as x and y. Well, let me just transfer symbols here. So y is really taxes, capital T, as it's indicated in the table, and income is capital I, minus 2149.5. Well, let's do some assessment, some diagnostic on this now. So it reports that r squared is equal to 0.9, about 0.98 we'll say, and r is equal to 0.99. Now just to prove that r, if you square 0.99, 1881337, you square that number, you should get the r squared number. So just as a frame of reference, you really only need to know one to get the other. Okay, well, r squared tells us that this is about a 98% goodness of fit. So that's pretty powerful. There's a pretty strong relationship between income and taxes paid. And r equals 0.99. The only important aspect that we want to draw out of this is the fact that it's positive. So what does that tell us? Well, going back for a second, that tells us that that a positive number means a positive relationship, which says that as the input increases, so does the output. So as income increases, so do the taxes. But that's no surprise. So realistically, we could probably look at the table and know that r should be positive. So really, this is the number that we want to focus on. The sign of this number can be valuable if you can't really tell by looking at the data, because it doesn't have to be all organized like this one is. Maybe our data is out of order, but the r will tell us what the relationship really is. Okay, so 98% goodness of fit. Now, what can I do with this equation? Well, number one, I want to interpret what this is saying. So I know that this is the rate of change and that this is the vertical intercept, or is part of the vertical intercept. Well, I know that a vertical intercept, let's start there, is of the form 0, comma, the value, negative 2149.5. Okay, well, wait a minute. What does that mean? Well, 0 is the input, and 0 is the income. So this is the income in thousands of dollars. And for that income, this would be the taxes paid. This is actually in dollars. Well, that doesn't make a lot of sense. So you're saying that if my income is $0, that I will pay negative tax dollars? Well, the last video we mentioned that not all values in the equation are going to make sense. So how do we explain this? Well, look at our data set. Our data domain goes from 20 to 90. So 0 is outside of that domain, right? 0 is actually, if this table were to go back, 0 would be somewhere up here. Well, anytime we're outside of our data domain, we call that extrapolation. So this is an extrapolated value, meaning 0 is outside of the data domain. And you can remember this by seeing the word exterior in the word extrapolated. Exterior, or extrapolate, extra, beyond. So it's outside of the data domain. And anytime we do that, we might get into dangerous situations. So really, what do you think we should do? Well, instead of extrapolating, maybe go a couple $1,000s above or below our domain, but we really want to just focus on interpolating. Okay, so interpolating is the same idea as extrapolating, except it's a value within our domain. So example, we know that our domain runs from $20,000 to $90,000. So if we're using to predict anywhere within this interval, this is interpolation. So I could plug in other words, 40 into my equation that I got and be interpolating. And then anything outside of this window, so anything less than 20 or greater than 90 is considered extrapolation. And that's just a term just referring to, are we using the data the way we should be doing? We probably shouldn't be going to like 170,000 because maybe the people who earn that much behave differently than the people who earn between 20 and 90. They may be in a different tax category altogether. Okay, so we interpreted our vertical intercept, which is just, it has to do with this idea of extrapolation, that a person earning $0 would pay negative $2,149.50 in taxes. But then let's talk about the rate of change. Well, the rate of change is always the idea of taking the change in output divided by the change in input. Now, just because we didn't do this doesn't mean it doesn't have a meaning here. So the change in output, well, what's the output? The output is dollars of taxes, or tax dollars. And the input was the dollars of income. Okay, so in this case, we have the number for the rate of change, the final answer, which is 188.2. So our change in output divided by change in input, when the calculator goes through this process, it does its little beep boop bop boop, and it finds that $188.2 of taxes per dollar of income. And excuse me, this shouldn't be dollar of income, this should be thousands of dollars of income, right? Because that's our income in our table is measured in thousands of dollars. So we pay about 188, on average, a person pays about $188.20 of taxes for every $1,000 of income. And I won't write that down, but I'll say it again. $188.20 in taxes for every $1,000 of income. And that's on average, right? That's not true for everybody, but it's true for kind of the average of all people. So if you know you're going to make a certain dollar amount, you can probably estimate what you're expected to pay. Well, let's go back to our calculator real quick, and we probably really should do this before we start talking about the data, but we knew that the R squared was pretty darn good. It was about 98%. Well, now when we go look at the graph and we look at income along the horizontal and taxes paid along the vertical, we actually do notice that the data points are really nicely compact around this line. So we would expect this to be a pretty close to 100% fit. Now you do have like this a little bit of a trend here, kind of dips down a little bit and then it kind of drops off more quickly than the line, but it seems like we have a pretty good fit here. So we assess that this is a reasonable model and we could probably use this to make some predictions. So let's just do an example real quick. How many tax dollars does a person pay? A person making 85,000 pay? Okay, well we know that that's going to be given by our equation, our regression equation, 188.2 minus 188.2 times the income plus, minus 2149.5. So there's our equation. That gives us the taxes. And so the taxes for an income of 85,000, which is already in thousands, so all I have to do is put in 85 minus 2149.5. Well, I can jump to my calculator, plug this in, go to my home screen here. 188.2. Actually, you know what? We can save ourselves a little bit of time because remember, our equation is already in the y equals. Perfect. So it's already there. I can just go to my table. And assuming my table is set up correctly, I can probably either set my table to start at $0 and maybe go up by 5s, or maybe have it start at 80 and go up by 5s. That way 85 should be the second number in the table. I'm going to set this back to auto. That way it generates the table automatically for me. And so at $85,000 I would expect a person to pay $13,847. And it's just these numbers are rounded, so if you want to see the decimal places, it's actually 13,846.71. So I would expect a person making $85,000 to pay about $13,846.71 in taxes.